let me remind you once again what we have covered so far. So, phase space and trajectory of a system through phase space. Then how do you turn differential equations into basically a problem of pictures. So, geometric way of thinking about something like du dt equal to f of u, and then concept of fixed point, which we also call equilibria and their stability. And how do you linearize and look at the slope of fu to find the stability. Right, and then so this is what we did in the first day, and then yesterday we looked at numerical methods for solving differential equations. I was tempted to write ODEs, and then I got reminded of an actual event which happened to me. So, there is a professor of Shah Institute, SN Bose Center. I will not name her because some of you may actually know her, who is known to be very aggressive. Okay. So, once she was giving a talk and she refused to take the, so this was a time when you used to use transparencies. So, she kept her transparencies in a plastic protective cover, you know, those grainy ones, and of course, when she puts it on, no one can see anything. So, people asked her, you know, we can't see anything, can you just take them out of the plastic protective covers? She said, I am not going to, you know, to risk the chance of ruining my transparencies for some bozos, and just kept giving the talks exactly like that. So, she is very aggressive, right. So, this was a smaller meeting we had gone to, and throughout the talk she is talking about ODEs, 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 ODEs and so on. At some point Jyotsna Dhawan, the famous biologist who was beside me, she whispers to me, I am too afraid to ask her, but what are ODEs? So, you know, I just couldn't help myself, I started laughing. Of course, I got a glare from the speaker, but Jyotsna got very mortified. She said, is it like I should know ODEs, and you know, is it something like, you know, like what is my name or something and I do not know it. I said, no, it's just that, you know, every field has its own acronyms which we assume everybody knows, but we forget that when we talk to a, you know, like a multidisciplinary audience, that others may not be as familiar with our terms. So, ODEs basically stand for ordinary differential equation. Okay. So, that is why I am trying not to use those acronyms, but if I ever by mistake write ODEs, you know what I mean. Okay. So, I just introduced Euler method, but then told you that there are other better methods, but I am not going through them simply because you will find numerical algorithms already coded somewhere. Okay. And then most important of all, I looked at bifurcations which are possible in one dimensional dynamical systems. And so, we found that there are only 3 types: pitchfork, saddle node and transcritical. And we used a few examples to illustrate this. Most of these are from ecology. So, for example, we used essentially the concept of population growth. So, we started from something like dn dt equal to Rn and saw that it will essentially blow up. So, then we went to something known as the logistic map, which will basically go to this equilibrium k provided R is positive. If R is negative, it will go to 0. And then for pitchfork bifurcation, we looked at this example that you can take something like a metal bar, and if you keep pressing on it, it will either fold this way or it will fold this way. So basically I can think of the bifurcation. So if this is my parameter and this is my equilibria. So I have something which is stable below the critical point. So this is also like essentially a phase transition. So you have one qualitative behavior below the fixed point and a different set of different qualitative behavior above the below the critical point, and another kind of behavior above the critical point. So because you have two solutions now instead of one solution, and the original solution becomes unstable. So something which I did not mention is that there is another kind of pitchfork which is possible. Okay. So that pitchfork is if you just replace all the stable lines with unstable lines and all the unstable lines with stable lines. Okay. So in other words, I could have something which looks like this. This kind of pitchfork is also sometimes seen. So what you have here is you have two unstable solutions and one stable solution, and then at this critical point they all meet and makes this stable solution into an unstable one. Okay. So there are these two types of pitchfork, and then saddle node was, we looked at this example of a ecological system with alley effect. So we found that if you raise this curve high enough, essentially what you have is something which was stable here collides with something which is unstable, and then you are left with only one stable point. So in other words, here you will find that this stable point meets with this unstable point, and this they disappear and only the stable branch remains. So this is basically the bifurcation of saddle node. And transcritical is where, so this is your parameter, right, and this is also your parameter here. Okay. And again you are looking at the equilibria. So now in transcritical what happens is, let us say there is a unstable branch here and a stable branch here, and then this becomes, they collide, the stable becomes unstable and the unstable becomes stable. Okay. So this is the example of a transcritical, and I gave this example of the logistic map as an example of transcritical. Okay. So this is what we have done until yesterday, and I was planning to go on to what is known as imperfect bifurcation, but we will have to do it today. Imperfect bifurcation, which is also sometimes called known as a catastrophe. I will show you why. Okay. And then finally we will go on to two-dimensional systems, where you will see how do we generalize now from what we have been learning so far about one-dimensional system, that is a single variable whose evolution is described by a first order differential equation. And then if time permits, we will very briefly look at a three-dimensional system where a new kind of behavior. So in two-dimensional system you have a new kind of behavior which will now become possible, which is oscillation, that is periodic activity. So previously in 1D system we saw that you can't have oscillations, but now in 2D periodic activity becomes possible, and then in three-dimensional system we will see that something different is again now become, not only you have oscillations and fixed point, but you can also have chaos, and we will briefly look at what is chaos. And because it is very hard to work with three-dimensional systems, we will use a trick. We will now, instead of differential equations, talk about difference equations or maps. They are also sometimes called mappings. So these are basically systems which are evolving in discrete time. So instead of dx dt equal to f of x, that xn plus 1 equal to f of xn. So they evolve in discrete time intervals 1, 2, 3, 4. And surprise, surprise, you can see that these are capable of showing chaotic activity even for a one-dimensional system. Okay. And in particular, we will look at the concept of a Lyapunov exponent, because this is something that Shagor would need when he teaches you evolutionary game theory in the second week. Okay. So, from the perspective of what you will need in next week, this two-dimensional system and the concept of Lyapunov exponent is very important. So, I will definitely try to cover these. If I cross my time a bit, please be patient, and I already ask Aninda for his forgiveness if I take slightly more time. Okay. All right. So, what will I do today? Anybody? In case you have been following. Imperfect bifurcations, right? Okay. So, what is an imperfect bifurcation? So, let me start with an actual problem, and again I will work with something which is ecological. Okay. So, so by the way, nobody has asked me, but in case you are curious, what is my source of wisdom? My Bible is this, Strogatz's seminal textbook on nonlinear dynamics and chaos. This is the original edition. There is a newer edition now. There is not that much difference between the original edition and newer edition. I think he has just one more chapter or something. So, I consider having a copy of this as important as a Bengali having a volume of Rabindra Rachanavali. Okay. I mean, if you are a Bengali, you have to buy Rabindra Rachanavali. If you can't afford it, at least have Gitanjali. Okay. I do not know what is the corresponding analog for other regional languages, unfortunately. For Westerners, I mean those who are religious, it might be having the Bible at home, but believe me, if you are a literate scientist, you should have this copy on your desk even if you do not read it. Okay. And if you do read it, I am assuring you, you will be amazed at the lucidity and the clarity of this book. It's the, I make no mincing of my words when I say this is the best textbook in any subject I have ever read. Okay. It's a wonderful book. Okay. All right. So, which is why I am not giving lecture notes. I mean, who needs lecture notes if you can read this? Okay. Just be aware of what I am talking about, and if you want to know details, just go and look this book up. Okay. But I will have readings. Okay. So, already there are 4 papers which Shakti has uploaded for today's lecture of mine, because these are papers which I will allude to in my talk today, and you should go and look up the original papers. Okay. All right. So, let us come to imperfect bifurcations. All right. So, example. So, many forests have this problem that they would have insects which tend to infest certain types of trees. Okay. We are all familiar with this in agricultural land. You suddenly have some blight happening to attack some agricultural crop, everything goes down. So, this is a particular problem for farmers, right. But even in forests which are by their very nature extremely heterogeneous, you could have certain insects, and one particular insect that we know of is known as the lurch bud moth. So, the name does not particularly matter. So, these insects attack a particular type of tree. Okay. Now, these trees are extremely slow growing. Okay. So, from the purpose, we can take the trees to be essentially, number of trees to be essentially constant. Okay. These evolve much faster, and so essentially we will be only dealing with the time scale at which the insect population grows over time. So, we can take the trees to be a constant resource and focus on the insect population dynamics. Okay. So, what people find is that there could be a very slow infestation of this, where a few trees get infections of these kinds of insects, and then suddenly, like without warning, almost the entire set of trees in that forest have gotten infected and then die. So this is almost like a discontinuous transition. Okay, so you have basically the insects occurring at some kind of a just about what you call sustainable level, some refuge level, in which they are just enough of numbers are there such that they can carry on from generation to generation, and then suddenly they are all over the space. Okay. So you might say, okay, maybe this is happening because of some climatic change. Okay. But the point is, how is this sudden abrupt change happening? Okay. Can we have some kind of a model for this? Okay. So first, how would you tend to model this? Well, you can say, okay, why not we go to our old friend. So if we call the insect numbers to be capital N, let's call dn dt, and we have the growth rate into n into 1 minus n by k. Okay. So this is our old logistic equation. Okay. If this was the only thing, then it wouldn't solve our problem, right? Because all we will see is that there will be a slow growth. So how does this evolve? We have, okay, if you solve this either you can actually analytically solve it, either analytically or numerically, you will see that it kind of grows like this and eventually settles to the carrying capacity. Okay. So this is not as abrupt change, all right. So what's going on? Well, then you talk to your ecologist friend, and your ecologist friend says, you know what, these insects get preyed upon by birds. Okay. And you say, okay, so that's like introducing a death rate to the insects, right? So maybe I'll put a minus dn. Okay. The only problem is these birds can also feed on other stuff. So they will only start feeding on these insects if they have increased enough in number. It's simply not worth their while if these insects are at very low numbers where they have to go and find out, like really seek out these insects. So unless like they have a yen for these insects, like these are like some really delicious insects or something, they don't really care. Only if it's so abundant that you just land on any tree or you just land on any of these trees and you immediately find lots of insects in front of you, do you feed on them? So how do we model that kind of a behavior? Any ideas? So it's not just putting in minus bn, right? It will have to be something else. Sorry? Okay, so let's think about it like this. What do we want? Suppose you are looking at it from the point of view of a bird. Okay. So you are saying that my feeding or how many insects I will feed on how does this go with n, that is the insect population. Okay. So initially when the insects are very few in number, I don't care because I have other food, right? Why would I go in search of this very rare insects when there's a lot of other food which is abundant? So I don't care, it's like effectively zero. Okay. Okay, what about when the insects are very abundant? Why constant? Good point, but why constant?
You can only eat a certain.
Exactly, right? So you won't just keep feeding just because it's more abundant, because at some point, no matter how good the food of our canteen is, not that I'm saying it's good, but let's suppose it was really delicious, there's only so much you can have, right? So you'll reach some kind of a saturation. It's very good. Okay. So how will it look in the middle? Do you think it will be discontinuous? In the middle, you are like, okay, if you are given one more fish, oh sorry, if you are a vegetarian. If you're given one more fish, at least if I'm given one more fish, I'll definitely have that one more fish. 3 fish, yes, okay. But if you give me 10 fish, okay, at least at this age, I won't be able to do it. Okay. So definitely it will be linear in some portion, right? So then you basically smoothly join this up and you see that you get a sigmoid. Okay. So how do I get a sigmoid?
Just an observation.
Yeah.
It's funny that you started from insects and went to the canteen food.
Did you find insects in your food by any chance?
Just saying.
No, this is a very sensitive matter with our institute canteen because we had a freshers welcome a couple of weeks back and a significant number fell sick. And there's a lot of speculation as to whether there was some insect, unintended insect in the food. So quite unconsciously we hit upon a very raw nerve.
I'm not sure if confidence is rising here in the room. Don't worry.
Well, so far no one has fallen sick, hopefully. Okay, so one way to think about this is, yeah, sure, I can put a sigmoid function. I mean, I can maybe put in some, hyperbolic function or something and properly scale it and so on. But you'll notice that one of the simplest ways of doing this is just to have a function like this. Can anyone tell me why this will behave that way? Or why do you think it will behave that way? So if it was bn by a plus n, how will it behave? If it was this form, how will it behave? So when n is very small, what can you do? When n is very small, basically you can ignore this n in a plus n because n is much less than a. So you can say it's b by a into n. That's a linear function, right? So it's linear. At very large n, you can ignore this a now. N is much larger than a. So it just becomes bn by n, which is just b, right? And so you know that this is going to be a hyperbolic. Okay. But if it's bn square by a square plus n square, now what happens is it's growing much slower than linear, right? A square function. Right? So it will grow like this, and then because at large values of n, what will happen is again you can ignore a square compared to n square. So it becomes bn square by n square, which is just b. So it will saturate. Right? So I know that I can model the feeding of the insects by birds, how their numbers are decreasing because of that, through this term. Now you might say, hold on, there's not just one bird, there are more. Okay? But if I take the bird population to be roughly constant, I can absorb the number of birds. So this will be into the number of birds, but I can absorb this into this constant. Okay? So everybody with me so far? Understood why I am writing it like this? Okay. So what are the parameters here? Parameters means those numbers which basically govern the behavior of the system but which don't change, which are things which I assign. So the variable is n, okay. So there is r, the growth rate, k, the carrying capacity, a is the half saturation, and b is basically telling me it's like some function of the number of birds into what is the maximum I can eat. Okay. Okay. Too many parameters. Okay. Can I decrease the number of parameters? So there is a technique called non-dimensionalization, which is very useful, but also very hard to learn. Okay. So I will just give you an example of non-dimensionalization, but not go into like how do you actually non-dimensionalize any arbitrary equation. But one thing you can do, you can look like this. So you can say, okay, I divide by b, okay, and I replace n by the fraction relative to the carrying capacity. So I call some quantity x, which is I replace it by some quantity called n by a, okay, which is this half saturation. I don't divide by carrying capacity, rather I divide by the half saturation, that is the value at which the value of n at which you reach essentially the feeding upon it to this. So basically this will be half, okay. So that's the value for which n equal to a. Okay, so why do I do this? So if I write like this, so basically I use these two things, what does this become? So this becomes, so n is now ax, okay. So this becomes a dx dt, but remember I have divided by b, so I have a by b. What about this one? So this becomes r over b, n can be written as ax 1 minus, okay, a by kx minus, and this is why I did this thing in the first place. So now since I divide by a, this b goes out, so I have n square by a square plus n square, but n is ax, so this becomes a square x square by a square plus a square x square. What does that give me? X square plus 1 plus x square. So that simplifies, right? So that just simplifies to x square plus 1 plus x square, which is the reason why I divided, why I use that variable, scale variable. Okay. Okay, now I will do another trick. So from calculus I know I can change variables. Okay, so what variables I will change? So first of all I will rescale time. Okay, so I will use some tau which is b by a into t. So this means d tau is now b by a dt. Okay, we will, so that will basically get rid of this quantity. Okay, then I will replace this r a by b with a small r. So this is a scaled growth rate. Okay, and finally the carrying capacity I will scale by a. So these are the replacements I do, or these are the rescalings you might say. Yeah, so a is the half saturation capacity, it is the value of n at which the amount that is being fed upon by a bird is half of its maximum capacity. Okay. It is basically controlling the slope of the sigmoid. Okay, so now what do I get? I get dx by d tau. So see, I have now gone from t to tau, this rescale time, and because I have gone there, now this b by a basically crosses out with a by b, so that is gone. Ra by b gets replaced by r, so it is x, and this k by a is small k, so this becomes small x by small k. So now what do I have? I have something, how many parameters? Just two, right? The rescaled growth parameter, so this is a dimensionless quantity now, and the rescaled carrying capacity. So this technique is known as non-dimensionalization, because now these are all do not have any dimensions. Okay, so now you take a look at this and start wondering, okay, what kind of behavior would this be capable of? So you know how this behaves. If you did not have this term, you know roughly how it will look like. So given any differential equation, what do you first look for? Fixed points, equilibria. So how will you find the fixed points for this? Hey, first you find the fixed points before you look at stability. Slope is your stability. You set dx dot eta equal to 0 and solve. Okay. So what will you get? So fixed points is obtained by 0 equal to, so I can take x common, right? X r into 1 minus x by k minus x by 1 plus x square. Okay. So, one solution of x is obvious, x equal to 0, right. What about the other value? Okay. Now, I can try to solve it, but I will use a graphical trick to find it. What is this graphical trick? It says that I have to find that x for which r1 minus x by k equals x by 1 plus x square. So, what if I plot these two functions and see where they intersect? Okay. So, what will x by 1 plus x square look like? For small x, what will it be? It will be like x, right? So, I know it's going to grow like this. For large x, it will look like 1 by x. So, it will look something like this, right? Okay. What about this one? What? Downwards, very good. So, where will it intercept? What will the intercepts be? So, this is R and this is P, right? Everybody with me so far? Anybody not sure about how this is coming about? Because this is just a line, straight line, okay? So, you just put x equal to 0 here and you find, okay, for what value will I get this? Yeah. So, for what value of this x equal to 0, I mean what will be the y? So, suppose this is y equal to r into 1 minus x by k. So, you say, okay, suppose I put x equal to 0, that is here, what value of y do I get? R. So, that is how r comes, and then you said, okay, I want y to be 0, so that means I set 0 here, so that is 1 minus x by k equal to 0, so that means x equal to k. Got it? Okay. Now, where do they intersect? Yeah, sorry, there was a question? No. Okay. So, now, so that tells me that, okay, there is a one solution, but hold on a second, r and k are parameters, I can vary them, right. So, I can actually take a r and k such that it goes like this, right. So, that means there are 3 fixed points. So, depending upon what is my r and k, I can get one fixed point, and okay, this is apart from x equal to 0, that is there, okay, or I can get 3 fixed points. Okay. So, what does that mean? Suppose you are here, so that means you have something which looks like this. So, you have a stable fixed, okay, so there is an unstable fixed point at 0, okay. So, you will have something like this. So, so you will converge to either this one or this one depending upon where in the x space you are located, okay. Now, forget about x equal to 0 for the moment. So, you look at this function, this looks vaguely familiar, right? Where have we seen this cubic before? Sorry? I can't hear you. Yeah, so good. So, I can say, hold on, it looks vaguely like a bifurcation I already know, but there is a slight twist to this, because now there is also the possibility that I can get only one fixed point, okay. So, for example, I can also have something like this, so that means you have a fixed point here and so on, right. So, this tells you that there could be a normal form for this, which is of the following form. So, the normal form for this particular kind of bifurcation is having the form dx dt equal to h plus rx minus x cube, okay. So, what is particular about this is that for r less equal to 0, you get something which looks like this, and for r greater than 0, you get something which looks like this when h is irrelevant, right. So, this is not very different from what you already saw in your pitchfork, Salon one, right. Now, what has changed is that now if you have h equal to 0, then this is pitchfork, right. So, for h equal to 0, you basically get this, right. Why? Because here you had a stable fixed point and now you have a unstable and stable. So, this is basically your pitchfork, okay. But what happens when h is not equal to 0? So, when h is not equal to 0, what is happening is you are raising the whole thing, right, here or here. Now, if you raise h, you will be intersecting it at some finite value, right. If you raise h, you will be intersecting it here, and then this 2 will come closer, and eventually if you keep raising h, eventually it will disappear, right. So, what kind of bifurcation will you get? So, you will have something which looks like this. As you change r. So, this is your equilibria x star, and this is how it changes with as a function of r. But now when h is non-zero, you see that you have this asymmetric behavior, okay. Now, what does this mean? Okay, you would say, okay, this looks like a complicated thing, but what does it really mean? Well, let's look at what does this mean in the r and k space, okay. So, in the r and k space, this now means that when k is small, okay, so that means you are just cutting it like this, you only have one solution, right. So, one stable state. But when k is large, so like you are intersecting it like this, you now have two stable states, or so it is basically bistable, okay. Now, you might ask, hold on, how is this behavior coming from? Where is this behavior coming from? So, can I see it in a 3D situation where I vary r along one of the horizontal axis, k along another axis, and on the third axis I am plotting the scaled population. Okay, question, how is this different from the previous bifurcations we saw? Or what is I said that there were only 3 possible bifurcations in 1D systems, but I left something unsaid. That unsaid part was there is only one parameter. Now, what has changed? There are 2 parameters. So, this is in the language of mathematics what is called a codimension 2 bifurcation, okay. So, how will it look like? Okay. So, if I plot it, it will look something like this. So, for k small, I have a x which gradually grows with r. For k large, I have something which looks like this. There is a fold, okay. And so, if you plot it like this, you will find that at some point this fold is going to unfold and become a smooth function like this. So, if you cast light on this, so imagine this is a translucent surface. So, if you cast light on this part, okay, where there is an overhang, see this part overhangs on this part will give you a darker shadow, which is precisely this, okay. Now, you might say, okay, big deal, what does this mean in terms of the behavior of the system? Can anyone say what this means? So here the population is low. So this is the so called refuge state of the system, of the insect population. Here the population is huge, it is the outbreak state of the system. Okay. So when you are here, when k is low, you have a very smooth change. Okay, it is like a continuous transition. When you are here, what will happen? As you change r, so here as you change r at low k, things change continuously. Here on the other hand, as you gradually move like this along r, you go here and then what? Suddenly there is a discontinuous move to the upper fold, and so you get a discontinuous change to outbreak. Now you might say, hold on, I mean there is a sudden outbreak, so your entire forest service comes into the picture and basically say, okay, how do I manage to bring down r? So you do something, you manage to bring down r to this point and nothing happens, right? It still stays stuck in this fold, okay? Because to get down here you have to come all the way here before it can change all this way, and so you get a hysteresis like behavior. Okay. So you can see that in the same system, just by changing one of the parameters, you can get a continuous transition or a discontinuous transition. Okay. Now,
can you repeat that last point again, like what you said, even during the outbreak?
yeah. So suppose you are here, you are just going continuously from a refuge state to a outbreak state. Here on the other hand, as you gradually increase r, suddenly you find that there is an outbreak in the system. So what will your tendency be if you are in charge of the control of the forest? You will say, okay, let me just do something so that I can decrease r to exactly what it was like the previous day. Okay. So you make a small change, but it won't bring you back, right? You have to do a lot more before you can get back to the system, and this is something which, you know, climate change activists are actually trying to make politicians understand, because politicians always think, oh, today you know, one more straw has not broken the camel's back, so I can add one more straw, and if the camel sags, I'll just remove that straw and the camel will become straight again. It doesn't work like that, right? Once the back is broken, you have to do a lot of serious surgery before the camel becomes upright again. And this is a perfect demonstration of that. Okay. So this should remind you of something if you are coming from physics, or at least if you were conscious during Rajesh's first lecture. See, Rajesh showed you this picture, right? Let me use the black. So Rajesh showed that if you look at pressure versus temperature, then you have this curve. So here you have solid, here you have vapor, and here you have liquid. This is the triple point and this is the critical point, right? So if you go around this, you can continuously change from liquid to vapor, whereas if you try to cross this, you get a discontinuous change from liquid to vapor, right? Okay. You also know that you must be also familiar with this, right? If you plot volume versus pressure, you know that at high temperature you just follow, what is this law? Boyle's law, right? But as you go to lower and lower temperature, you have a region where there is a coexistence of two phases. Okay. So if you are going from, let us say, vapor to liquid phase, there will be a coexistence phase in which gradually the entire liquid will turn into vapor, during which it will remain, the temperature will remain roughly constant, right. So, sorry, this is happening through temperature. So, this is just happening by your decreasing pressure. So, the pressure will remain roughly constant until the whole thing turns into a vapor, right. Okay. And this point is basically the critical point. Now, as you notice, these are two projections of a three-dimensional phase diagram: pressure, volume, temperature. Okay. What does that look like? So, the moment I draw it, you will realize what is the connection with this. So, now I will draw. So, along this axis I have temperature, along this axis I have volume, and along this axis I have pressure. Okay. So, you will find that this is actually behaving like this. So, at high temperature it behaves like this, and then you might say, okay, it does not look anything like this, but if you take the van der Waals equation of state and if you solve this, basically you find that it is going to give you a cubic. Okay. So, just look at this one and look at this one. At high temperature you have the continuous transition, at low temperature you have exactly this kind of a curved overhang. Okay. So, why do not we get the cubic in the case of the liquid gas transition? That is because of the Maxwell construction, because this part is unstable, and so we replace this with a flat part by using the Maxwell construction. Okay. So, if you are not from physics, do not worry about this. This is just for the people coming from physics to tell them that they already knew this codimension 2 bifurcation, they just did not know that this is a codimension 2 bifurcation. Okay. So, again another connection between statmech / thermodynamics and dynamical systems. Okay. All right. Now, for people from psychology, Pritha is here, right? Ah, yes. A fun analogy. So, there is this very nice book by someone called John Allen Paulos. Oh my God, seriously, it is already 3:30. Any possibility we can take a class tomorrow? Do you think we have time? Because I need to actually cover 2D systems. We also started late. I should not say this because I am an organizer. So, there is a book by John Allen. So, he is a mathematician who writes wonderful books on the use of mathematical literacy. So, just as you have illiteracy, a major problem, he calls mathematical illiteracy innumeracy, and he said our society's main problem is innumeracy. Okay. Because people who would have feel ashamed if to admit that they can't read find no shame in saying, oh, numbers, I do not understand them. Okay. He said, how on earth are people okay with not being conversant with numbers? Okay. So, he actually has a book called Innumeracy about why maths education has to be completely overhauled to make people numerate. Okay. So, he has if you really are into this, you can read his books called A Mathematician Looks at the Newspaper, where he talks about how when you look at a newspaper, the media has very nice ways of hoodwinking you by actually telling you the truth, but you don't, I mean, we can't really visualize millions and billions. So, suppose someone says, the taxpayer will be losing billions of dollars because of this 4G scam. I don't have an intuition of what is a billion. Okay. So, how do you actually get an intuition of what a billion means, right? And then he has an even more funnier book called A Mathematician Looks at the Stock Market, which is about him going into the market thinking, here I am, a really good mathematician, surely the market can't hoodwink me, and how he gets completely creamed. Yeah. So he writes this book about these wonderful ways that even if you are a mathematician by profession, you can get completely hoodwinked by some very, very simple stratagems that the market uses. Okay. So for example, I can't resist giving one of the stories. He says, suppose I want to run a scam on you. All I need to do is the following. I send letters to 1 million people saying, I have a perfect system for predicting how a stock will move. I know you won't believe me, so before I ask you to invest in me, I will give you 3 free predictions. Okay. So you say that stock X will move. So to 500,000 you say up, and to the other 500,000 you say down. Okay. Now next week stock either moves up or moves down, right? So suppose it moves up, you forget all about those half whom you said it's down and focus on that 500,000 whom you said it was going to move up. So now you send a second letter. See, I told you. Okay, I will give you the second prediction. Stock Y will move to 250,000 you say up, to the other 250,000 you say down. Okay. Okay, so let's say next week that stock moves down. You forget all about that 250,000 whom you said stock will move up. So now you send a mail to this 250,000 and you say, third tip, stock Z will move, and to 0.25 million you say up, 0.25 million you say down, right? Okay, now forget all about the 0.25 million whom you said the wrong prediction, and now focus on the remaining 0.25 million and say that nothing in life is free. I gave you 3 tips, now you have to invest. Now you have to buy my system. Okay. Now that 0.25 million is now completely convinced that you have a foolproof system, because you got 3 times you got it right which way movement, and if they're still unconvinced, you can actually do this the 4th time, and which you bring down your 0.25 to let's say 0.125 million, right? And now you charge, just a minute, now you charge them and say, I will give you a like blowout sale price, because you are my the initial customers, and I know many people are trying to buy, but it's a Black Friday sale, right? And so you only have to spend 10,000 rupees. Okay. So now 0.125 million into 10,000. Just imagine what a killing. Why do you need to invest in stock market when you can make a killing like this? Yeah, sorry.
No, I have a feeling that this is how astrology survived for generations.
I didn't say that. Yeah. But yeah, you're right. There's always this bias that we always believe those events which actually came true and forget all about the millions of times that they actually failed. Yeah. Okay. So sorry about that thing, but I just couldn't resist that. Paulus is a very favorite author of mine. But the book that I'm talking about is not that. This is one of his earlier books. It's called Mathematics and Humor. So the book is about, can we try to understand why a joke is funny using maths? Or what is the essence of something which we perceive as laughter inducing? Okay. When is a joke, right? And so the book is actually fun because he gives lots of very nice examples. There are really interesting cartoons. So there's a picture of a man in a raincoat, the typical dirty old man, who's come in front of a young woman and says, under what set of conditions is propositions A, B and C true? This might seem, what am I talking about? He says the typical joke where like some guy comes and makes a sexual innuendo where he says what comes in hard and what goes in hard and comes out soft, okay, and then he will say chewing gum, right? This is nothing but precisely, you can take all of those jokes and basically they fall into that class under what set of axioms would conditions A, B and C true. So you say D, but he said no, E. Okay. So reduced to its basic structure, the joke is nothing but that, and you can form a whole set of jokes just using this structure. So the book is about all of these kinds of things, right? But the one chapter I like best is where he gives an example from this imperfect bifurcation or a catastrophe. So he said often a joke is like this. So a joke falls flat when your realization of, so like you are expecting something and then your expectation is suddenly altered, that's when you start laughing, right? But if it a person, how you deliver the joke also matters. So a person when mangles up the joke, your realization is like this, and so no laughter ensues. But a person who tells the joke well, you are being led up the wrong path and suddenly the perception switches, and at the incongruity of it all you start laughing. Okay. So he gives this example. So he says, okay, it's a bit like this, that you have a system which is like this. Okay. So when a joke falls flat, you are going continuously, but when a joke is successful, you suddenly jump from one realization to another realization. But then in order to motivate this, he comes up with a completely different example. He said, imagine the behavior of a dog. Okay. So a dog can have two parameters of fear and rage, and the dependent variable is aggression, the level of aggression in its behavior. Okay. So if it has too much fear and less rage, then it will fight or flight. If it has too much rage, little fear, fight. Okay. What will happen if it has a lot of rage and a lot of fear? Okay. So this is, you are gradually increasing the fear, and so its level of aggression drops down, and so you get flight. Here rage is gradually, sorry, I should have drawn it like this, it should go like this. So when your rage is very high, you get fight. But when both fear and rage are very high, a small perturbation can cause the system to either switch from flight to fight, or from fight to suddenly turning its tail and running away, right? So I find this incredibly interesting, because to some extent this shows why behavior can suddenly change. You have this Assad's military forces holding strong for 10 years, and then in 3 days flat they fall, turn tail and run away. All right. Now I know this is very simple, and this is precisely why catastrophe theory got bundled out of the universities, because people like Zeman, who were like great acolytes of catastrophe theory, started saying sociology is dead. Okay. Now with catastrophe theory we will be able to predict prison riots, we will be able to predict why people fall sick, why people are depressed and so on. So no need for the psychology departments, no need for sociology departments, we will just have maths departments. So of course this hyperbole got them really angry, the psychologist and the sociologist, and the first opportunity that they got of showing that catastrophe theory got something wrong, there was a huge fracas in the press. Gina Kolata wrote an article called "The Emperor Has No Clothes," about how catastrophe theory is all just big hype and there's nothing really inside, and catastrophe theory is now a forgotten science almost. Okay. But they had something really incredibly cool. Okay. Now I will just end by saying that So one of my hobbies is reading a lot of military science. As you all know, Bengalis are a martial race, right? So, so I spend a lot of my off time or down time reading military history, military psychology, and so on. You know, you always have a fascination for things which you can't have, which you don't have a hope of doing ever, right? So there was this book I started reading called War Games. So this is a very serious book on why people fight, or in this particular case, don't fight. So one of the big problems for armies is how to ensure that the people actually kill people, because you know this ingrained thing that thou shalt not kill apparently is very hard to get rid of. So the entire concept of boot camp in the military is not to train them, it's basically to destroy all your inhibitions to the point where you will do exactly as you're told. Okay, so if you are told to kill, you don't start thinking about is it justified, is it moral, what did he do ever to me, and so on. You just follow the order. Okay, so that's the concept of boot camp. But this guy, who is actually a former military officer, says that after interviewing lots of soldiers and commanders and so on, he has come to the understanding that it's not just fight or flight. That's too simplistic. There are other kinds of behavior, for example, freeze, and this is a major problem. So often people will just refuse to take orders. They are just, they're just like zombies. Okay, so the commanding officer is telling them, get out of this trench, go and do this thing. Doesn't care. Okay, so he is frozen essentially. And there's another very interesting behavior which he calls fuss, which is you keep doing something which is completely pointless over and over again. It becomes like a ritualistic thing. So like he talked about a Vietnam War veteran who said that I was supposed to command this particular platoon. Instead I just like a OCD just kept cleaning my rifle. Basically it gave me a like I could separate myself out from this thing that was going all around me. So I'm just like obsessively I'm just cleaning my rifle. Okay, another person was just bringing grenade from one point to another point. He said, of course my platoon didn't need all those grenades, but I found a sense of purpose in just doing this grenade instead of actually taking my gun and shooting people. So this person said that actually there are 4 kinds of behavior. It's not just fight or flight, it's fight, flight, fuss, and freeze. And so one of the things that I have in my mind is how do I modify this so that I can get this 4 different kinds of behavior in the simplest possible codimension, the most elementary codimension bifurcation. So that's something, if you are ever interested, might want to think about. Okay. How do I modify what was basically just a fight or flight discontinuous response into something which can also capture these other 2 kinds of behavior? Okay, so what I will do is I will maybe take an extra class tomorrow.
Yeah, either the morning or the afternoon, we can decide.
Okay, so because I really need to tell you about the 2-dimensional system, which is what is actually remaining, and so that it sets the ground for Shagor's lectures next week. Okay.